what about today? So the first, say, half an hour is going to be really some like blah blah, just warming up. I'm going to show you videos and very few equations, and then we're going to start to introduce a list of concepts. They are basically the main ingredients of statistical learning theory, which is the framework we use. And then after the break, we're going to encounter the first basic set of algorithms, namely local algorithms, and the whole idea of model selection, which is another word in what I was about to say parameter tuning, which is one of the annoying things you have to do when you use machine learning algorithms. So as I said, the first part is really just very high level. And I just want to give you a vague idea of what is machine learning. And of course, this is going to be a biased and personal perspective. And the thing, hopefully it will emerge, is that there are somewhat two words. One is the word of intelligent system and artificial intelligence, and one is the word of data science, which is a fancier way to say essentially statistics for data analysis. And these two words somewhat collapse. Okay, in the last few years, they somewhat start to converge. The techniques that allows you to develop intelligent system and the techniques that allow you to do data analysis start to blend in some way. And if you were to say this to people probably like, I don't know, when artificial intelligence was born in the 50s, this will be completely come as a surprise. Okay, and hopefully at the end of these next few slides, you will see it's not much of a surprise. And this is one of the ideas. Machine learning is the thing that stands in the middle between artificial intelligence and data analysis in a way. I just want to start with a very brief story of like snippet of story of where artificial intelligence and machine learning come from. And one probably cannot avoid noticing that we have no idea how to define intelligence. Okay, there is not a smart way of doing it. And by now, to some extent, we do accept this proposal that was done by Alan Turing of basically just giving an operational definition of intelligence, basically advocating the one kind of intelligence we assume we know, which is our own intelligence. Okay? And so the idea here, do you all know what is the Turing Test? Most of you probably know, but here, the idea here is essentially that you have a human interacting in some way through a device with not humanoids like computers, but some kind of artificial machine. And if the human is not able to understand or to realize he's interacting with a machine, it means that the machine passed the Turing test. Very high level, this is the idea of the test. And as soon as you try to be a little bit, you say, oh, this is very rough, let's try to be a bit more precise. And you immediately start to see there's going to be a pretty long list of things the machine needs to be able to do to deceive the human. And here there's just a little list. There's probably it needs to be able to parse and understand a bit what the language is and the meaning in the language. It probably needs a way to memorize and represent information in some way. Probably needs a way to reason in some way. He needs to learn, provide him with an experience that he hasn't had before and need to be able to adapt to the new experience and to react to the new experience. And then you can start to make it a bit more complicated because you can send something like a picture maybe and ask what's in the picture, okay? The whole idea of CAPTCHA, that's the name of the thing. They're making it complicated, and now they're making it, they just show you a picture, and you're like, you're kidding me? That's an apple, okay? But a machine is not really able to do it too much these days. So that's kind of one other way to go in the direction of intelligence. And then you can make it even harder. You can, if you start to have a physical interaction when you can pass object and things like this, then you will need the artificial entity to have some kind of capability, for example, manipulate things and things like that. So the interesting thing is that to some extent, each of these in the years has become a separate field, okay? Oftentimes not interacting with each other. And we'll see a bit why. The reason why these things are very small is because all the details are not important, but this is just a list of names. As I always say, like if you go to a machine learning cocktail party and you want to just drop some names, these are probably the ones that you might want to remember. People like poor thing, Rosenbluth is not written like this, Rosenblatt. Is Wiener, Neumann. I think von Neumann and Turing are probably among all of them the 1-2 people that somewhat are recognized to be the starter of this whole discipline. Especially lately, because we're happy because things start to work, so we can look at our shames in a bit more of a confident way. People often recall this one meeting in 1955. Do you know about this Dartmouth College? Anybody knows about this? Nobody? So what happened is in 1955, a bunch of people, and here I wrote very small their names, decided that they were going to solve artificial intelligence in a summer. They went to Dartmouth, which is a beautiful place, and they decided to get a bunch of people like you, and they said, okay, you guys are going to solve computer vision, and you, natural language processing. You guys can do robotics, okay? Done. And then by the end of the summer, we're going to build artificial intelligence. So it's laughable now, but this gives a sense of, these people were not laughable at all, okay? And this gives you a sense of how much we just miscalculated the entity of, no, I'm going to let them alone, poor thing. No, John McCarthy, Marvin Minsky, Claude Shannon, and Nathan Rochester. So Marvin Minsky, I think, is a well, all of them are actually super big shots. But so this gives you a bit of an idea of how much people just completely miscalculated the entity of the problem, okay? They just thought it was easy, and it turned out that it was super complicated. And this is one first thing that is like is like the beginning of the story. Another thing we give you a beginning of the story is that one other thing that came out is that things that for us are complicated, and we thought they were very complicated to do, for example, playing chess at the master level, we were able to solve quite a long time ago, almost 20 years ago, okay? Whereas, as you see in a minute, things that for us are completely trivial, we are not able to solve with machines at all. So these two facts, the fact that our preconception of how hard it was to build intelligent machines was completely wrong, and then the things we thought were hard were actually kind of easy, and the other way around, are two aspects of the story of artificial intelligence. This is a short excerpt of a video I stole from Tommaso Poggio, and this is research that was done in his lab 10, 15 years ago, more 15 than 10. And here you see a first system to detect pedestrians, okay? Basically, the system would be shown a bunch of videos, and then after some processing, would basically, at runtime, try to put a square around people when it would see one crossing the street or walking around. And what you see here is that he's doing a fairly decent job. It's a small snippet, so it's not significant. But you can see also that basically sometimes where there's some stuff which is elongated, it would just put the square around it, okay? And seems to be convinced that that's a pedestrian. So it was working okay. And it was around that time that Amnon Shashua decided that he was actually going to put a company, and I apologize for those of you who have seen this video that I show every time I give this presentation, and basically set up a company that would make these things really work. And he's been working in the last few years doing this. Now his company is in the stock, so it's going pretty well. And this is now a system that you can buy in commercial cars. It's an optional, like air conditioning, okay? And it's a system based on vision. And here just a little ad. All right, so the systems work and work really well. It's sold, as you can imagine, it must work really well, because imagine it doesn't work, okay? And if you actually kill somebody, you can be sued for a lot of money, and the company would be done overnight. So the fact that this product is actually in the market means that this thing is remarkably reliable. And the system basically works at 99.9999999% of success. So this is like one example of how are we doing today, okay? We do have this kind of stuff. Let's see if I can show you this.
Voice recognition technology in a lift in Scotland. You ever tried voice recognition technology? No, they don't do Scottish accents. 11.
Could you please repeat that?
11.
So this is, I guess, his common experience of a few years ago, and this is an ad for.
Imagine if everyone talked at the same speed that they typed. Now imagine if everyone typed at the same speed they talked. Now you can.
So this is kind of where we are today, okay? So we have stuff that actually works. The one that I will show to my mom, and she's really happy, so I'm going to show it to you too, is this one here. Some of you might have seen it, but surprisingly many people haven't seen it. So let's go. D'ora in poi il corso sarà in italiano. It's not my fault.
That's right, it's called the Jackson.
From now on, no, it's an internet problem. We're in a bunker.
From now on, the course will be in Italian.
All right. So you can go on vacation and speak whatever language you want, and it will translate you.
Va bene, così posso andare in vacanza e parlare qualunque lingua che si desidera e sarà tradurre.
So this works actually pretty well. So it's pretty much Google Translate with Siri or whatever is Google Voice on top. So it sucks the same way Google Translate sucks. And it doesn't suck that much. I mean, I think if I'm going to be, next time I'm going to be in Vietnam, like it was last year, and nobody was going to speak English, yeah, it probably is okay. I can ask where is the restaurant, where is the bathroom without, you know. So this actually works pretty well, I think. And this is where we stand today, okay? It's kind of an exciting time to be in the field. And the number of people in the room, I think, is another proof. The number of companies that are born every year and acquired by other big tech company, the number of people that start to attend machine learning conference, it's a huge proof of the success of this kind of thing. So it's kind of a good time to do this kind of stuff, because for the first time since probably the beginning of artificial intelligence, we're far from understanding what intelligence is, or even from just replicating in some way, in a complete way, but we do have snippets of intelligence which are good enough to basically augment our capability to interact with the world and solve potentially complicated questions. So what I want to show you now in the next few slides is just the first example, giving you a vague idea of how we do this, okay? What is one of the ingredients? We actually many ingredients and go and make these things work, especially in this kind of hard applications. But this is just one, look, there is an M. What are the ingredients that go into these systems? And basically there are two main things. What changed? What changed in the last 20 years? Well, mostly that we got very good computers and a lot of data, okay? But the other things that perhaps we can, I convinced myself that happened is that now we have also has techniques that allow to process this data with computers and try to answer complicated questions. So here is an outdated list of things that can be done. And the idea is that machine learning is this set of techniques that are basically learned from data rather than explicit program to do a task. And so you see where data start to come in. You essentially try to provide answers like those you would like to obtain, and then you have the machine somewhat inferring what are the rules, what are the techniques that are needed to answer these kind of questions. And here, as I said, there is kind of an outdated list of potential application. And here in the corner in particular, you see things which are essentially plots and data visualization. They not particularly have to do with machine intelligence, but they're actually kind of data that you treat it exactly the same of techniques that allow you to do things like, for example, voice recognition. So I'm going to try to start with a very simple example stolen from Coursera, and you bear with me for a few minutes, and then we start to move on to something a bit more interesting and complicated. So everything starts with data, okay? And the one simple situation is this situation here where you are given observation of houses, dimension, and prices, and given this, you would like to predict the price of a house in the future, okay? So for a while, you record how big is a house, and then you basically say, okay, there's a new house. I know how big it is. So you record how big is the house and what is the price. And then you're given a new house. You know how big it is, and you want to give it the price. Okay? How do you do that? Suppose that I give you a new house which says 2,000 square feet. How much do you think it should cost? How do you solve this question?
Linear regression.
Linear regression. But suppose that you're not even that good, okay? How would your mom solve this question? Experience. That's a bit black magic. Like,
A proportion.
like what?
Like I can take, like you say 2,000.
Yeah.
I can take 3,000, and it's 540 divided 3 for 2.
Why not 14,000?
Because it's my mom, and she can't do that. And then
She just took the last line.
yeah.
I'm gonna tell your mom you said that. But my mom, what she would do is that she probably would take the house which is closest in size. Okay, that's the simplest thing you can think of. You say 2,000. Well, let me check. Oh, this one is close enough, so it's gonna be somewhere around there. Okay, that's a mommish way of solve the problem. And we'll see in a minute. This is actually an algorithm called nearest neighbor. Okay, it's what we're gonna see today. Linear regression is much harder. We're gonna see it tomorrow, actually. So this is the basic idea. And so the basic idea is that we start to have some symbols. You have some inputs. I call it x, and outputs, y. Okay. In this case, the inputs are just the dimension of the house. So x1 is this number, xn is the last number, and y1 is this number, and yn is this number. So far, so good? In this case, I can plot these things. So I can put here the size of the house and here the price. And you can even just try to solve this graphically. And okay, we can try to do that. Suppose that now you really want to solve this problem, okay? It's not just a game. There's something truly naive in the way we're trying to do this problem. Suppose that you really want to give the right price to a house because you want to become rich. What is the first thing that we start to do to improve this system? Doesn't look too smart. But not because of the way we solve the problem, but probably because of the data. This is not very rich, right? So what is that you would do to improve this? Say it again? How do you want to increase the data? So somebody said increase the data, but how do you increase the data? More samples. So this would be, each one is a sample, is a pair, and it would take many, 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 many more. Absolutely yes. Anybody else has other ideas?
Consider other characteristics.
Consider other characteristics of the house. I think this is actually probably going to do a big difference, right? So you say certain amount of, you consider a certain space and time chunk of observations, and then you look at number of rooms, if it has a view, if it has a balcony, if it is central heating or not, air conditioning. You start to write all this stuff, okay? For example, here's just an example where you look at the rooms. And here you really see that things can get complicated. These can be real numbers. These can be essentially natural numbers. But the main thing this example want to show you is that it's fairly natural to keep this one column as it is and start to add other columns. So this x now is what? x1 is going to be what? It's going to be this number and this number. Okay? So I'm going to use always the same notation. I'm not going to put little arrow above my symbols, but sometimes they're going to be arrays. And in this case, x1 would be an array made of these two numbers. And x2 is going to be an array made of these two numbers, and so on and so forth. Okay? Can we draw this? Yes. But as soon as you start to add other stuff, you might not be able to inspect the data anymore, because this can become, say, 2, 3, 4, 6, 10, 100-dimensional array that you're not able to visualize anymore. Can we still solve the problem the way my mom would solve it? What would my mom have done here? Well, if I give you a size of the house, you would check the closest size and assign the same price to the new house, right? What is the equivalent things you have to do here? So the new house, you're not only going to have the size, but you're also going to have the number of rooms. Then what do you do? Right, you still, the only things so he said you search the closest one, and he's absolutely correct. And the only thing is that what you mean by closest, because before you just have a number, and now you have to find some way to measure distances between not numbers, but array of numbers. So for example, you have to say if this line is closest to this, then it is to this, for example. And here, for example, you can just take Euclidean distance. You take the difference of each numbers and take the square and sum it up and take the square root. Okay? Or you can invent something fancier than that. So everything will go in the way you define close, but conceptually you can solve it in exactly the same way. But you start to see one trend, which is that you start to go from low-dimensional problems to potential high-dimensional problems, where here the dimensionality refers to the dimensionality of the input space. Okay? So this example might seem oversimplistic, but if you get this example straight, this is like contains pretty much everything conceptually of what we will want to do. So the game we're going to play in the next 3 slides is basically that we're going to change the setting, the examples, and we're just going to try to see how we can fit the different problems into this framework where there are x and y. We're going to ask what is x, we're going to ask what is y, and at some point, once we have this, we forget how we got it. And we just, for example, just see how we want to measure distances, and we're just going to solve the problem. Okay? Is this clear? Any questions about this? If you're lost here, you're lost. So this other example is, so the game we want to do now is we take one problem and we try to fit it in this x and y business. So the problem here is, let's say, detect whether an email is a spam or not. Okay? So imagine that you have a situation where you spend a few days, and whenever you get an email which is a spam, just click spam and throw it into a folder, and otherwise you keep it in your main directory. And after a while, you have these 2 folders, the main directory and the spam folder, where you have a bunch of texts. Okay? And what you want to say is, once you get a new email, we would like to say if it's a spam or not. So the first idea could be, oh, I'm just going to put rule. If it contains Viagra and something else, probably it's a spam. But the thing is that, or if it's a king of Kenya that wants to give me 2 million, that's probably also spam. But then tomorrow it's going to become the king of San Marino, okay, or the king of whatever. You're going to change just a little bit, so you have to be robust. So you want a system that is able to adapt, okay? So that's why we want to use learning, to adapt to the different situation and learn in a varying way what we mean by spam. So we want to try to use exactly the approach before. So what's going to be the output? Before it was what we wanted to predict was the price of the house. What is that we want to predict now? Spam or not? So it's actually going to be a Boolean output or a binary. So 0, 1 or -1, 1. Okay? So it's not a real number. It's just one of 2 possibilities. What about the input? How can we turn a text, okay, into a vector of numbers? If you already know it, don't cheat. I saw. Yeah, but then if you know bag of words, you're cheating. But now it's too late. You spoiled it for everybody. So bag of words is the way you do it. So the way you do it is basically that you take a bunch of text or a dictionary, okay, and you just write this long list of potential words that you can find in all possible text. It's going to be a very long list of words, okay? Then what you do is the following. You check the first word, and you see if you find it in your text. If you find it, you put 1. Then you check the second word. If you find it, you put 1. If you find it again, you put 2. And so you just do counting of words. What is going to be the most frequent numbers you find here? 0, because most words, this is going to be a long dictionary, so most words will actually not appear. So this is going to be a very, very, very long vector, because a dictionary can be pretty long, and it's going to mostly contain 0, but it's going to be very, very high dimensional. So if this is now a text, each of these numbers is going to be the occurrence of a word in the dictionary. Okay? And another line is going to be another text. That make sense? To some extent, now we're done. Because now this is x and y. X is occurrence of words. That's what is called the bag of words. And the output is just going to be 1 or -1. Given a new text, you first check which words appears and you turn it into an array. And then once you have that, you try to predict whether it's going to be a spam or not. Okay? In practice, by the way, people don't really do this. What they do is that they really do something like this, but they typically have a pre-processing that cut the word to the root, so that begin, begun, beginning, beginners are actually cut to what you call a root, the beginning, which I guess is begin. And this thing actually works surprisingly well, okay? If you think about it, it's a pretty rudimentary way to represent a text. You destroy any grammar, syntax, a lot of the semantic, well, semantic no, actually, a lot of the syntax in the text, but it actually works pretty well. If you want, for example, do sports versus politics, this is typically enough. If you want to say whether somebody, I don't know, if it's Wordsworth or Shakespeare, then it might get a bit trickier, okay? If you want to say if it's more romantic or less romantic style of writing, if you're going to go to these more complicated hues, probably something like this would not be enough. But if, for example, for topics, it works pretty well. And they made some tests where they take a text and they scramble it and they show it to people. And it seems that actually people can do the same. If they just have to figure out what is the vague topic of a document, they're good with just a few keywords, which is basically what's going on here. And point us to one of the key of the whole story we're going to see, which is we actually have to deal with very high dimensional data, but we kind of hope that one way or another, the number of important things in the data is going to be so many. So in this case, the vector is long, 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 but perhaps there are a few keywords in each text that are going to matter, okay? Oh, I don't want to see this. I want to see this. So this is another example. Same game as before. We state an example and we try to fix it in our XY framework. Here the example could be I have images of, say, the letter 0 or O, I don't know, and then Z, okay? And the plan is that once I have one of this or this, I just want to say whether it's O or Z. And of course I have a bunch of observations where I do know the answer. So again, in this case, we can think of a situation where the answer is binary, say is one or the other. How can we turn an image into an array of numbers? Not the smart way. Say it again? That's too smart. Say it again? What's the first word? I don't understand. Numbers. Yeah, so you just unroll the image. The image is going to be a collection of numbers, and I think I even have a picture. All these pictures, by the way, are stolen from somebody. I almost never do a picture. So if you zoom in an image, you're going to see a collection of numbers. If it's black and white, it's going to be between 0 and 255, 6, one of those. What you do is that basically you take all these numbers and you unroll them. Okay, you put one line after the other, and you just turn an image into a long vector. It sounds like a good idea or not? Not very much, right? Why?
Because the quality of images are different, so it's going to be very...
Yeah, so one reason is because you might have images of different quality, okay, or different size and so on. Let's say that you normalize them all. You scale them to be the same size. I still think it's a bad idea. Why?
Because images more than text are organized by a structure. There's a geometry in the image. So
right, so absolutely. So what he's saying is that image and even more than text have some kind of structure. So when I take this, and when I take this and I put it afterward, I'm destroying the fact this is actually close to this in some way, okay? Surprisingly enough, and in fact, this kind of naive way of treating the problem won't really work on a hard problem, but you can actually give it a shot and see that if you're just going to consider the distance, the Euclidean distance of these two vectors, this order won't matter, okay? You're just going to compare this guy with the, corresponding, one pixel with the corresponding of another image, another pixel with another corresponding of another image. And so if you're just going to just do some simple distances, this won't matter. And this simple method actually gives you something decent. Not great, but would actually something decent. When I say decent, it means that with respect to your typical intuition, I say this will never work. Well, take a bunch of my images and a bunch of Carlo images and just try to say, compare distances. Okay, it won't work great, but it actually does a decent job, which is another take-home message of this kind of stuff. And it's like one great motto of machine learning. First, always try something that is naive, okay, and oversimplistic, and see what you get with there. So that once you're smart, you can actually show that you're smart, and you're just not recovering something simple in a complicated way. The main point that we want to observe here, aside from these remarks, is that this vector is, again, potentially very, very, very high dimensional, because it's as big as the number of pixels in an image. And unlike the one before, this won't be sparse. It's not true at all that most of the numbers in here are going to be 0. Most of the numbers here are going to be some value of the pixels. Okay? And here again, we observe this kind of situation where if here n is the number of what? Images or pixels? And p is going to be the number of pixels, and you might be in a situation where the number of pixels is huge. Okay? And in fact, today we start to have a situation where also the number of images is huge. But typically, one difficulty is that you have to deal with extremely high dimensional vectors. Okay? So things like the linear regression that you learn in high school or early on in your college studies, it's become a different word. It's become this case where the dimension of p could be, I don't know, in the order of thousands or even tens of thousands if you start to extract more numbers. So how do we deal with that? The last example I want to make is the example from biology, and it might be a slightly outdated example. The idea here is you have a bunch of patients, and you have, for each patient, some measurements of the expression of genes. So what you want to do is that the patients are divided in two cohorts. One is disease type A, disease type B, and you want to be able to disentangle these two classes. When a new patient comes in, you want to take a sample of tissue, measure the expression of the genes, and based on that, predict whether this is going to be most likely type A or type B. Okay? So same game as before. This is just a picture of what is a microarray. Essentially is a technology to measure the gene expression. And roughly speaking, what you have is that pixels in this image, the intensity of the pixel, roughly speaking, correspond to the gene expression. Okay? So you can basically turn the intensity of a pixel here in expression of a gene. It's not quite like that, but pretty much. So what you're going to have here is that each of these is going to be a patient. And each of these is going to be the expression of the first gene of the first patient, the second gene of the first patient, and so on and so forth. The output, again, in this case, could be, say, 1 or 0, or 1 and minus 1, just whether it's type A or type B. So again, in this case, the number of observations can be huge. And one challenge in biology, for example, is that oftentimes these are people and these are diseases. Luckily, sometimes it's hard to collect samples, which means there are not that many people with the disease. Or worse, which means that hospitals don't agree on sharing data. So sometimes you have 50 patients, and then the number of genes you have in the orders of tens of thousands. Okay, so now you might have a situation where this is 50 or 100, and this is 50,000. Okay, so from just a basic calculation of degrees of freedom and number of data points, this seems hopeless. And so one question is, how can we go around this curse of dimensionality, which is this idea that you have many more observations than, many more dimensions, many more parameters than observations. So this is just to conclude this little snippet of how you somewhat frame many different kind of problems into supervised learning. That's how we call it, okay? You basically have many different problems in which there is an art step, which is look at the problem and think how you want to squeeze the problem into this X and Y framework. Then from that moment on, try to develop methods that are somewhat blind to the nature of the data and try to find ways to separate them in classes or predict a real valued output. Okay, so this class is going to be about the challenges and ways of doing this kind of stuff. So again, we start from the basic housing price example to move on to text, images, and biology. And what you see that these data are very different, okay? And in fact, you will have to put some extra information to solve the problem well, but we're just gonna, at first sight, just see how you can phrase them in this way. So far, so good. Any questions? Complaints? Yep.
Well, actually, about could you please, once we talking about the topic, add some external source we can rely on, like the Coursera course that you mentioned?
Yeah. But So this is what I showed you at the beginning. So basically the material here, so these are just examples. So pretty much I collected them on Wikipedia kind of style processing. So you just go around and look at stuff. The main, the reference I showed you at the beginning, in the one page at some point, they contain this. So the elements of statistical learning is one possibility. Coursera is another possibility, though I only stole that example, so I don't know what else is there. Yeah, these two I think should be enough, especially at this level.
Like talking about the name of the course, because there is a number of them.
Oh, Coursera is machine learning.
Okay.
Yeah, when I say Coursera, it's entering class on machine learning. So those two references should be enough. And in elements of statistical learning, they go on and on with a bunch of examples, okay? Other comments? So, and here is kind of what we wanted to get at, which is, even in these just few examples you've seen, there are some of them you feel more like talk about intelligent system, and maybe some others, like the biology case, where you talk about more data analysis, maybe. And what you see here is that, again, to some extent, what we want to talk about is the kind of statistical techniques that allow to go from the data to some form of decision making or information retrieval. Okay, data mining. These are all kind of synonyms in my head of the things you do once you get rough data. And the important thing is these rough data are never a complete picture of the world. They're just a snippet. And out of those, you want to extract, or if you want, generalize, and be able to get a picture of what is the phenomenon, the model, the world that generated that data. Okay, this is going to be our game. And the challenge is going to be high dimensions and potentially massive data sets to interact with. In some sense, machine learning is statistics with a computational twist. Okay, you are going to use a lot of statistical ideas, but together with optimization and an algorithm idea to be able to handle in a computational feasible way large amounts of potentially high dimensional data. Questions? So before killing you with the questions, I'm going to show you a couple of videos. This is really more a break, okay? So if you have any question you can think about while entertaining you with songs. This is work done at MIT a few years ago. Up. And this is, again, apologies if you've seen this. Do you know this song? It's from a few years ago. So this is Dido. And this is not Dido, just the song is Dido. So this is an artificial system. What it does is that it records, so you basically feed the system with a few minutes of a person speaking, and it learns the way the person moves the mouth, okay? The rest is superimposed, is engineered, okay? The eyes, the movement of the face, that's engineered. But the way the mouth moves is learned. The system is much more complicated than just deciding what's X and what's Y, but that's one of the ingredients. This is work done by Tommaso Poggio and Tony Ezet quite a few years ago, like 15 years ago. So what you should notice is that the letters are pronounced correctly, okay? If you hear the word and then look at the lips, they actually pronounce the right letters. And here I'm just going to show you a few examples. So this is Mary, it's her voice and the way she moves the mouth. The snippet of video I think is a bit longer than this. And once we have it, we can have Mary singing. But we can also have her singing in Japanese. Or Chinese. But so the video of Marilyn is much shorter, and so the quality, if you see here, is not as good as Mary. Mary is actually pretty good. Marilyn. So let me tell you what this says first. So this Rima Ellis is an anchor woman from, I don't remember which station in the States, and she's gonna basically, well, hopefully you understand, because otherwise I've been told.
Technology can take
Angeles, NBC News, Cambridge, Massachusetts, and New York.
So I'm not sure how much you hear. So what she says is basically that the new technology can process anybody's voice and make it come out from anybody's mouth, okay? And the next person you're going to see is Rima Ellis. All right.
The meeting was frank.
So this is actually, so that was mostly done for fun. And as I said, the last one for is a lot of fun because there is a lot of nice syncing of the movement of the face with the song. But the scientific part is really more the lip movement. So this is actually a small Turing test where they actually took a snippet of the real person and the artificial person and tried to see if people could actually recognize them. So if you see they're fairly short, they were shown.
The meeting was frank. The meeting was frank. 53%. 53%. More news in a moment.
And basically with this kind of little test, what you see is that people are not really able to recognize. This was not a lot of people. I think it was around 20, 30 subjects. And basically what you see is that there are 50% chance of saying whether this person is the real one or not. Of course, if you give them much more time and they start to study the thing, they probably will be able to caught up small imperfection in the video. But at this level, in some sense, Mary passed the Turing test. All right, so the meaning of this first hour or so of lecture was just to give you a vague idea of potential applications of machine learning and the way to cast different problems into a common framework. A lot of the art that goes into solving the problem exactly will not go in the classes because, of course, this is problem specific. So we're going to try to extract some of the general principles that you can apply once you cast your application in this XY formulation, which is what we call supervised learning. Okay, so that's what we want to do next. Just to wrap up this first part, the two things I want to mention is, as I said, this is a moment where a lot of high-tech companies are jumping on this kind of techniques, and basically Facebook is opening offices in Paris and New York essentially to do artificial intelligence and machine learning. This guy is Demis Hassabis. He's the boss of Joel, who's coming in a couple of days. His company was acquired for a ridiculous amount of money by Google a couple of years ago. Twitter is doing the same. So the trend right now is basically that each high-tech company is, Google has huge artificial intelligence group. It's endowing itself with essentially artificial intelligence and machine learning group. So there is a lot of opportunities there. But the other thing is that in the meantime, what you see is that to some extent, both in Europe and in the States, there is a substantial amount of fundings and efforts put in the scientific side of the story, because as you see from the application I show you, while we can legitimately say that computers do have some form of intelligence, the idea of robo-killers and the singularity is not quite there yet, okay? We really don't have a good understanding of what intelligence is. We are not able to replicate a full intelligence system, but not even that. We are not able to replicate a system with two kinds of intelligence, speech and vision in a decent way with a common software. Energy consumption is a huge problem. Amount of data is a huge problem. Most of these systems, the one that works, are based on the fact that companies such as Google can collect ginormous amount of data, which are now at disposal, but is also very costly. And if you're not Google, it might be very hard for you to get the same kind of data. So the challenge is out there, and one of the reasons why we're here is to try to contribute to it. And this is basically where I wanted to get it. And I said, this is just to warm up and start to think what we're talking about when we're talking about machine learning, okay? And what I want to do next is to move to the next part. So any questions so far while I change my slides? Question, comments? But somebody's awake because it's so dark. All right. So what we want to do next, okay, is a step for. So right now we introduced examples, but the only symbols we introduced are X and Y. We want to put a little bit more juice in what we're doing, okay? Oopla, oh, this doesn't work. So we're going to look at this system which are based on learning from examples, which basically means the idea of having these, mostly this input-output relationship and try to extract some decision-making or predictive rule out of this data. And you can consider this problem in quite a few settings. We're going to consider what is called the statistical learning theory setting. And the main idea is, again, that you have some kind of input-output relationship, some F, okay, that you would like to learn. And the key point is that you have some you have some data that you've seen in the past, and you typically call this set of observation from the past the training set. Again, n is the number of observations, and x here can be an array, okay? Typically is an array of numbers. So in the spam, images, text example, this was always a big array of numbers. And what you want to do is to learn an F, but very importantly, you don't care that much, although you do in some way, and you'll see in a minute, to predict this data, but you really care about making predictions about the future, okay? You don't want to be able to predict very well the data set you have on your laptop. You would like to be able to create a system that once new data comes in, and you don't know why, you can predict why well. A new email comes in, and you don't know whether it's spam or not, and you're going to say, well, you try to make a prediction where it should be one or the other. Similar, you get a picture of, you got a picture and you say whether it's me or Carlo, okay? So one key observation here is that it's obvious, but if you want to basically say that the data can give you information about some unknown functional relationship, you have to explain a bit better what is the connection between the data and the functional relationship. You have to assume that there is a model of your data, because there is no such things. You cannot really start asking the question. And a key point here is, this word here is uncertainty. While you do try to find a deterministic relation between input and output, you basically, once you get an email, you would like one way to basically say whether it's spam or not. This actually, the relation between input and output can be intrinsically noisy, okay, or affected by various kind of perturbation that make the problem uncertain. So you need a way to cope, on the one hand, with uncertainty in the data, and on the other hand, with the possibility of potentially making errors. And the game is not going to be being perfect, but it's going to be make the least number of errors as possible. So we need to make this concept. And again, the other point is going to be that the errors are not going to be so much on the data you have now as much on the data you can see in the future. So we'll need to introduce a way to model uncertainty, a way to measure errors, and a way to measure errors now and in the future. And once we have that, we can probably state what's the problem. Okay? So that's what we want to do next. Oh, this doesn't work. So basically, the next few slides are going to be extremely boring, and I'm going to give you a long list of names. So I'm just going to try to attach concept to the names, okay? So as much, if you question the names, is the best way to try to see if you can remember them in the future. The first bunch is fairly simple. We're going to assume that the inputs are coming from some input space, and the output are coming from some output space. The input space doesn't have to, but we're typically going to assume that it's actually vectors, okay? It's RD, it's just array of numbers. And the output is going to be typically a subset of the real numbers, perhaps just two values, say -1 and 1. And we call the product of this space the data space. That's where we get data from. We haven't done much so far, okay? So there is the input space and the output space. Turns out that if you change the input kind, you don't change the name of the problem, but if you change the output kind, you actually change the name of the problem in a way, funny enough. We typically call the problem where the outputs are real numbers, regression. And we typically call the problem where the outputs are binary, say -1 is 1, but this is just arbitrarily, binary classification. The generalization of this to many possible outcomes, and we only touch briefly upon it, is what you call multi-class, where you basically, instead of just two kinds, you have t possible kinds. Say, recognize faces not only between me and Carlo, but between me, Carlo, Alessandro, and Giulia. Okay? This step is very important. What we want to do is introduce a big new concept which has not been out yet, and is the idea that in the data space there is a probability distribution, okay, that relates the input and the output. It's a joint probability distribution between x and y. Basically, everything we don't know about the data, we put it there. The key point is that this distribution, we assume it exists, we assume it's fixed, but we don't know it. All we know is the data x and y that are sampled from this distribution. Okay, we know n pairs, x and y, each one sampled from this distribution. This is a purely theoretical step, okay? If it's useful, it's useful. If it's not useful, you should drop it. It's an assumption. It turns out that it's pretty useful in many situations to guide the way algorithms do work. Not only we make the assumption that the distribution exists, we also assume that it can be split this way. And once you split it this way, you start to think of x as an input and y as an output. And as I said, here we put in the distribution P, we model everything we don't know about the data. Once you split it this way, for example, what you can see is that if you fix x and you look at the conditional probability of y given x, it basically means that if I give you an x, I cannot say for sure that there's going to be a y associated to it, but there is a whole distribution of possible values. Some are more likely than some others. That make sense? So you can think of this as some kind of noise on the relation between the input and the output. The nature of this noise, the word noise might be misleading, because you might have a situation where, for example, literally you have an image and you add noise, okay? But you have a situation where I stole Carlos' glasses and he grew a beard and we actually look alike. And then you will have the situation where two things get close to each other, and that's also some kind of probabilistic effect, but it's not perhaps what you would call noise. Or you might have a situation where you have images and you just put a very low resolution rate, and so basically by compression to have some form of noise, which is more of a perturbation, some form of, say, probabilistic blurring of the identity of the image in the image, but it's really not, again, what you would call noise. It's just some other kind of perturbations. So this comment is just to say, sometimes I call it noise, but really a lot of different stuff goes into this distribution that connects the input and the output. Does it make sense? Okay, this is a very important conceptual step, assuming this distribution. The other thing we can do is look at the marginal distribution, the distribution of the input, okay? And you can think of this in many ways, but the easiest way is to think of essentially, say, when we sample the space of images, okay, or the space of houses, you might not be able to have a very uniform sampling for some reason, okay? And you might just see some samples and not some others, and you would like to make prediction everywhere. And so this actually gives you, for example, there might be some area where you're more likely to sample images or houses than some others, okay? And this is modeled by this. It's nothing to do with the price of the house, nothing to do with whether it's, say, it's an image that contains myself or Carlo, but it's only the fact that, for example, I don't know, there might, if you want to say, you want to predict the temperature in this room and you want to put a bunch of sensors, there might be points that are easier to get than some others, okay? So the distribution of sensors in the room might not be uniform, okay? And so here you put all this in determination. And this list is really a partial list of the potential things that you can shove in here. On one hand, you can complain and say, well, but these are all really very different things. Why do we put them all in the same basket? Right, well, because you can see how far you can go putting them in the same basket and see how much you can treat all these problems in the same way. There might be points where it really pays off to say, oh, no, look, this is really quantization, it's not noise. Or this is really semantic confusion in my data, it's not compression, okay? But for now, we're going to just put everything together and see how far we can go. The basic example of distribution, okay, the basic example of data that are sampled according to distribution is this one here. You're probably going to see it in the lab. Or maybe not, I don't know. In fact, you think you're going to see this. Fix a function, okay? For a minute, you're God, okay? You know the function f star. You know the noise. This one is a random variable. This x is also a random variable. Say you fix the interval 0, 1, take a uniform distribution over 0, 1, fix a function, say the sine, and then just add Gaussian noise. And then you get the number y. Do this several times, and this is going to be a bunch of x and y's. The relation between x and y is not deterministic because it's completely governed by the noise. And the f star tells you to some extent what is the best choice in hindsight if you could know the model of the data. This is what one would call the regression model. The distribution over x and epsilon defines the distribution over y. And this is going to be your joint distribution over everything. Okay? So this is the basic special case of what I just showed you. It's a basic way to define a p of x comma y. And that's what you do in the classic case of regression. Okay? And these choices are completely arbitrary. Okay? This might not be a Gaussian noise. It might be a Poisson noise or any kind of noise. This is just one example. In the case of classification, notice that y typically has only two values. Okay? For example, 1 and minus 1. So you're not having a lot of possibility for your output, and these two are related. The probability of one given x is 1 minus the other. The case of somewhat a noiseless, quote-unquote, situation in classification is the one where the probability is always either 1 or 0. It basically means that the relationship between the input and output is not really probabilistic. It's equivalent to the case where epsilon here is 0. Given an x, there is a right answer. And here it would be the same. If the probability is 1, it means that it's Lorenzo 100%. If the probability is 0, it means that absolutely it cannot be me. Okay? And here you will see in the lab different way of building this kind of situation in a very simple way. So the data model, we assume that we have this probability distribution. We can split the distribution and see that we can put noise and sampling as well as many other effects inside this distribution. And here are two main examples, regression and classification. So I forgot. So one thing I didn't say is a slide disappeared, but I want to write this at least once. An acronym that you will hear a lot is IID. It stands for independently and identically distributed. It describes the way the samples are assumed to be generated from this distribution P of xy. And it's a very important assumption. It means that when you see x and y, these pairs that you get in your training set, they always come from the same distribution that doesn't change over time. It's always the same. There is one P of xy. It's fixed, unknown, and you just can take samples from it. Okay? I'm emphasizing this because there are a lot of situations that is clearly not true. Time series is the classical example. A process that inherently changes over time in a substantial way. And this is the first I, identical. Okay? You always come from the same distribution. The second I is independent. When you take a sample, the next sample is going to be completely independent. They're not going to influence each other. Okay? And the second assumption can be relaxed in many possible ways. The first one, so I think it's crucial up to a point. The first one is really crucial. Because as you will see in a minute, the fact that we assume that there is just one distribution fixed a priori will basically tell us what is the ideal solution of the problem. If the distribution does change over time, there is no such thing, and the problem gets much more complicated. So in some sense, the independence assumption can be relaxed. This identically distributed assumption, which is, if you want, is some form of stationarity, is really crucial. All right, so the next step, as I said, is, so this is where I promised you three things. Introduce the model of uncertainty, that's what we have just done. And then basically introducing a way to measure errors because we look for a deterministic relationship in an uncertain environment. So we have to accept the fact that we might make mistakes. And so the loss function, the notion of loss function, is what formalized this idea. And in words, a loss function basically says you get an x, you predict f of x, but then you're told that actually you should have predicted y. How much do you pay? What is the basic example of loss function? Say in the house pricing example, okay? You're given a size of the house, you predict the price, then you reveal the true price. And you want to measure how much mistaken you are. What would you do? The difference can be positive and negative. So what would you do? The absolute value or the square. One way to make it positive. Okay. This is the least square loss function. And it's arguably the default choice in a lot of problems. What about classification? If you have to make a decision whether a picture contains me or Carlo, okay? So now I got your picture, you predict me, and then you revealed it's Carlo. How would you pay an error?
0, 1.
The simplest way is 0, 1. You just say, if I was right, I'm going to pay 0. If I was wrong, I'm going to pay 1. We'll see in a minute that this loss function, which is basically what is called the misclassification loss function, is very nice theoretically, but in practice leads to unfeasible problems. So we'll have to treat it in some way. So the loss function is good because it gives us a way to measure error. The problem is just it's an error on a fixed x and y. And I don't care about the fixed x and y. I want to be able to talk about the error I will make in the future. Because ideally, that's what I would like to control. And for this reason, one introduced this theoretical object, the so-called expected loss or expected risk. In words, what it says is take the loss function and then now average over all possible y and x. Okay? So here there is just the expression. It's an integral because x and y can have continuously many values. If you are bothered by the integral, just think of it as a sum over all possible values of x and y. And here you have weights. The weights that basically say, if I get a couple xy, which is very likely to be sampled, this should cost more than a couple xy that never shows up, even if they have the same loss. Okay? Can you compute this quantity? Depends. It's a democristiano answer.
By definition, we don't know the probability of x.
Say it again?
By definition, we don't know the joint distribution.
Yeah, so by definition, it absolutely depends. But for today, because I said loudly that I'm going to assume that this is fixed but unknown, you cannot compute it. Okay? So unless you are in a God mood where you actually generate your data or make strong assumption, you won't be able to make any calculation about this. Yet, this is the theoretical object that it will tell you something like, does it exist an ideal solution to the learning problem? There isn't an optimum I can shoot for, okay? And the optimum would be something that makes this small. If there exists an ideal solution, it will be the one that makes this error small, which basically says that I can do well in the past as well as in the future, in all kind of x and y that I may be able to see. And we would call this a target function. It would be in some sense a minimizer of that. Okay, so again, this is now an important conceptual step. We introduced uncertainty in the problem, and now we say we introduce a theoretical measure of error, which is the ideal one, is the one where you can average out over all possible x and y. This will not be particularly practical, but the moment where you ask things like, does it exist an optimal choice of the parameter of my problem, of my algorithm, we're going to split the answer in the question in two. First, you're going to be a theoretical, you're going to be a theoretician and ask, does it exist? What does it depends on? And you will need concepts like this to be able to have a framework to say what does it even mean to be optimal. And then there will be a separate question, which is as and more important, which is how do you do things in practice? Okay? So this will be our framework to cast all mathematical questions, and then we'll try to see how this framework suggests way to solve the problem in practice. Hoopla. So just because I don't have it on the slides, an object that we will often use in practice is the empirical counterpart of the expected error, which is the quantity we obtain if you replace the integral, the expectation over all possible x and y, with the sum over the training set points. Okay, so the difference here is that I have the x and y that I have in my training set, and I now can compute this quantity. I just have it. Once you give me an f, I can compute it. So oftentimes, this will be the quantity that we'll use in practice as a proxy for that. Okay, this is something you can compute. And in some sense, there's a whole theory that tells you that we will not touch upon much. It tells you to which extent this is a good approximation of that. Yep.
What about the joint probability?
Say it again.
What about the joint probability?
It's hidden in here. So let me give you the hand-waving version, and then we see if it's needed to write an equation. When you write the average, what you can do is that you can take all your samples, all of them, and sum them up. Or you can divide it in groups with the same values, and now sum over the possible values and put the frequency of each value. Okay. Here I use the first version, where I take all the samples and put them all together. Suppose that I have points with the similar value. Okay. So the values of y and x, the possible value of this couple are v. In practice, it won't happen, but let's assume for a second it does happen. Then what you can do is that you can do the sum from 1 to v, and here you have, well, you have to put the weight of that couple, okay? So in my way of, so this is equal to 1 over n this is one way to write an empirical mean. This is another way to write an empirical mean. Here is sum over all observation. Here I just sum over all possible values. Here you don't see the weight, the density, and here you do see it. Okay? So just, this is very easy. So just think 1 second about it offline, and if it's not clear, you let me know. Okay? Yep.
Could you please explain again the IID acronym?
So it's, so the words are identically and in.
I mean the assumptions behind the
First thing first. The name is identically and independently distributed. So identically means that every pair xy comes from P of xy. You can assume a situation where you get a pair xy, and then somebody changes the distribution P and gives you P prime. Right? This won't happen because all the examples are identically sampled from the distribution. Independently means that when you get x1, y1, this doesn't influence the probability of getting x2, y2 with certain values. So these two samples are completely independent. That's it. Okay? So you can have a situation where you put a camera on top of this door and you have people entering, and probably these samples are quite, so this is, say, over a course of this class, you're going to be always you, and this is probably going to be always the same distribution, more or less. And the fact that she enters or the fact that he enters, let's say that it's independent, okay? If you want to predict the fact that it might be sunny or rainy, that's probably not the kind of situation where samples are identically and independently distributed at all. You can still wonder if you, by making this assumption, you can get something useful, and that's a different story. But clearly, it's an assumption that might be violated in a lot of situations. Good. Any other questions? Not a lot of questions, I have to say. Yeah. I'm assuming because everything is perfectly clear. So now, a few names, okay? So let's recap the names so far. The probability distribution, we don't give it a name. Loss function is one name, or cost function. I think economists are actually optimistic and call it utility function, but we call it loss function because we are existentialists. Then we call the quantity we can define over all possible pairs expected loss or expected risk. And we call this guy empirical risk or empirical loss. It kind of makes sense. We give a couple of names. We call the procedure that given data returns an approximation f of s of my target function. We call the procedure learning algorithm. And we call the function fs estimator. It's an estimator of the target function. Okay? Let me point out here that this terminology is kind of annoying a bit because it doesn't quite make a distinction. In statistics, people call estimator a theoretical procedure and don't really look at computational aspects. Okay? So what I mean is, learning algorithm So what I want to put the emphasis is that there's going to be always two ingredients in what we do. On the one hand is the principle, statistical principles that allows us to do some kind of estimation. And then we have to say what are the computation entailed by that principle. Okay? And so in some sense, when I think of a learning algorithm, I would like to keep into account both aspects of the story. So what is the kind of principle, what is the objective, what is the kind of procedure I want to do, and how much it costs me. And I would like to see both aspects. Because there might be, for example, a procedure which is optimal, but I cannot compute in practice. The way around, there might be something which is very cheap, but it's not very good. And so we want to keep into account both these aspects. And so the learning algorithm part tries to, the learning algorithm name tries to keep into account both these aspects. A fairly important point is that while we assume that the target function exists, we are not really interested in estimating the target function, but rather to do as well, meaning that the target function is going to make a certain error, and we would like to do an error which is more or less as big as the one of the target function. In which case we say that the solution generalizes. If it generalizes, if it predicts well in the future. One possible way to do this is basically saying that my f of s, the one that I pick on the data, the real one that I can compute, should be close to f star, but not in every possible value, but with respect to the error. So this is the expected error, okay? Again, this is not something I can do in practice, but it's something that theoretically I could require. If my solution would have this property of make this small, my algorithm would be good. So typically, once you invent an algorithm, then you try to show if it somewhat is able to put your solution close in this sense to the ideal solution. Okay, so this is more the theoretical side of the story. Now, here there's something missing, okay, from a mathematical perspective. Because this makes sense. In words, this says the error of the ideal error of my solution is close to the best possible ideal solution, the best possible ideal error. But the thing is that this guy is random, okay? So different data sets will provide me different things. So now what does it mean that I make this small? Do I make it small for one specific data set? For all data sets on average? I have to specify in some way what does it mean. This is a random quantity. So if I want to say that this has to be small, I have to say in which sense. And the easiest way is to ask for this to be true in expectation, which means that for the average training set, or for the training set on average, my solution gives me a pretty good solution. Okay? This means that might have bad cases, okay? Or that my solution sometimes can be very different. But on average, it's fairly good. Yes?
Why you like use the optimal F and not just try to find the F that minimizes the expected error? Like without, I mean, I don't understand why the F star is.
F star is the one that minimizes the expected error.
But I mean, if you have the expected error, which by definition is the minimize like the error.
But the expected error is just the error. And the F star is the one that minimizes the error. Okay, so the expected error is just this. So given a function, it tells you how many mistakes you'll do in the future. F star is the one that minimizes this.
So yeah, so when you search for the F s, I don't understand why you need the F star. Just look for the F s that minimizes the expected error.
Yeah, and suppose that I give you 1, and I ask you, is it good or bad? How do you do that?
Well, we cannot do that because
no.
we don't have the.
But we are being theoretical now. Okay, so we're just trying to introduce quantity. So what I mean is, these are just theoretical quantities, and you will see in half an hour how we use them, okay? But what I mean is, suppose that theoretically we want to try to say what is a good solution or what is a bad solution. So you define the problem, you say, oh, the problem is to minimize the expected risk, and ideally I have F star, which is the best of the best. Then given data, I provide f of s. And then I ask myself, is it good or is it bad? I plug it in here. I go and check, ideally, the error. But then I still have to know if I'm far away or not from the best possible.
I still don't see why I need f star if the error of my fs is low.
How do you know what's low?
Because
is it 50 low, or is 5 low, or is 100 low? If you know that the best is 5, 5 is low.
Yeah, but it doesn't matter what is the best I can get. I mean, the best is as low as possible, right?
But but what I mean is, in some sense here, again, we try to define what is the quantity that somewhat we want to measure to see if we're far away from being the best or not. And so you need to find F star to basically, which is the lowest possible quantity. Suppose, for example, they want to check if polynomial is better than Gaussian, okay? Or say that linear regression is better than nonlinear regression. If I can show that constantly, this distance of the distance of one to the best is always bigger than the distance of one to the other, this is one way to say that one model is always potentially worse than the other. If I don't have something to refer to, I'm missing like what's the zero. I'm missing what is the reference point of this game. Okay. You will see in half an hour when we try to understand the behavior of one such algorithm, how having F star helps out. Okay. Yeah.
This just postpone the problem. I mean, if you have a distance of like 5, is that high or low?
So this is what does it mean?
So even if you compute this distance from the optimum, you still have a relative value. You don't know if that number is high or low, higher or lower. I mean, ideally, like the F star would be 0, right? Like the best you can get is making an error of 0.
No. No. For example, let's check this case. For example, okay. Suppose that I build the data this way. No matter how I do it, F star, which is the best, you can check that it's the best here, is always going to be affected by an error. It's basically going to be y minus F star x is going to, on average over all possible y and x, is going to be epsilon. So you always have an error. Okay, so you always have, because the relation between input and output is not deterministic, you're going to have a certain probability of making an error, and that's it. Even the best function is going to make an error. So this is still true that I might consider a relative error. I can divide everything by EF star. But for now, I'm just being simplistic. And all I wanted to say is, if you put your theoreticians at, you introduce the quantity you would like to minimize. Ideally, you would like to prove that your estimator is, you say that your estimator is good if it's close to the best possible you can do. But to say what does it mean to be close, you have to be a bit careful because the quantity you're dealing with is random. And so here you just say the simplest thing, which is it's low in expectation. Okay, I'm late. Let me just check how much fat I have. Okay, let me say one more thing and then we stop. In practice, again, we're being theoretical here, okay? So we introduce the quantity we would like to minimize, and then we just introduce two basic ideas. This stuff is basically going to appear and disappear. It's just going to be a reference, okay? We say that the algorithm is consistent if, as you give more examples, it's going to try to get close to the best possible. And if this error goes to 0, we say it's consistent, okay? This is a basic requirement. It basically says if you get more data, you're going to get closer and closer to the best possible solution. On the one hand, it's a basic sanity check. On the other hand, it's an asymptotic statement. It doesn't tell you how many points you need to be that far away from the best possible solution. And so if you have learning rates, or if you want finite sample complexity, it means essentially that you're able to make statements such as, if I give you precision epsilon, you will need these many points to be close epsilon to the best possible solution. And this gives you more information. So these are kind of guarantees that one would like to put on top of a learning algorithm. Okay? So what we want to try to understand, so now we just define what is the ideal problem we would like to solve. What I want to do next is, does this help at all in trying to understand how to design learning algorithms? Because for now we just said what is a learning algorithm and in which sense it might be good. But we haven't said at all how to build one. And we'd like to know how to build one and how to understand what are the properties of this learning algorithm. And that's what we want to do next.